students, welcome back to the chapter Coordination Compounds, and let us continue our discussion with valence bond theory. As we know, valence bond theory tells us about the hybridization, which tells us about the geometry of the complex. So let us utilize valence bond theory for some other complexes. Taking example of cupra ammonium sulfate, which is represented with the help of formula CuNH3 4SO4 2 negative. In this case, the ligand is NH3, that is amine, and it is a neutral ligand. That means the charge present on NH3 is 0. The metal here is copper with atomic number 29, which makes the configuration to be 3D9, 4S2 and 4P0. Now let us write the configuration with the help of orbital representation. If you see here, we have 3D, 5 orbitals. It contains 9 electrons. Let us fill all the 9 electrons here. After that, there are 2 electrons present in 4s, so it becomes 4s2. Now after this, let us find out the oxidation number or the oxidation state of the metal, that is copper here. Assuming the oxidation number of copper to be X, now the charge present on NH3 being a neutral ligand is 0 and the overall charge is 2. Therefore, the value of X comes out to be 2. Now since it is plus 2, that means copper is losing 2 electrons, and these 2 electrons, they are lost from the outermost orbital, that is 4s2. Therefore, 4s2 now becomes 4s0. So the configuration becomes 3D9 and 4s0. Now if you see here, NH3 is a strong field ligand, and we know that a strong field ligand is the one which supports pairing. That means if we have any unpaired electron, they will get paired up in the presence of a strong field ligand. But in this case, we have only one unpaired electron, and there is no other electron present with which it can get paired. So in this case, this one unpaired electron goes to the next higher energy level, that is 4p0, now becomes 4p1. Now we have 4 ligands, that means we require 4 orbitals or 4 vacant orbitals. So in hybridization, what are we utilizing? We are utilizing 1 from D, 1 from S and 2 from P. So the hybridization here becomes DsP2 hybridization, and for DsP2 hybridization, the geometry is always square planar. Now can we see here any unpaired electron? Yes, we can. So if you see here 4p0, 1 unpaired electron, which makes this compound paramagnetic. Okay, moving on to the structure of this particular coordination compound. As just said, the geometry is square planar, so that is how it is being represented. This is a square planar geometry. Moving on to the next example, that is hexamine cobalt 3 ion. The formula is CONH3 positive. The ligand here is NH3 again, which is a strong field ligand, which is a neutral ligand, so the charge is going to be 0 here. The metal is CO, that is cobalt, with atomic number 27, so the configuration becomes 3D7, 4s2, 4p is 0 and 4d is again 0 here. Now looking at the orbital representation, we have 5 orbitals for D having 7 electrons, 1 for S having 2 electrons. So let us fill the electrons over here. There are 7 electrons in D and there are 2 electrons in S. Let us find the oxidation number of cobalt in this particular coordination compound. Assuming the oxidation number to be X, the charge on NH3 is 0, overall charge is 3, that means the value of X will be plus 3. It means it is losing 3 electrons. Obviously 2 will go from 4s, so your 4s becomes 0, and 1 from 3d7, so it becomes 3d6, and therefore you get the configuration to be 3d6 4s0. Alright, as mentioned earlier, NH3 is a strong field ligand. It will support pairing. So if we have any unpaired electron, they will get paired up. If you see, we have 2 unpaired electrons, so they get paired up. Alright, now we have 6 ligands, that means 6 vacant orbitals are required. So what are we utilizing here? We are utilizing 2 from D, 1 from S and then 3 from P. So therefore the hybridization here becomes D2sp3 hybridization, and for D2sp3 hybridization, the geometry is octahedral geometry. Okay, can we see any unpaired electrons over here? No, that means it is a diamagnetic coordination compound. And the geometry or the structure can be represented here. This is your octahedral geometry for this particular coordination compound. Moving on to the next example, that is hexafluorocobaltate iron. In this case, the formula is COF63 negative. The ligand here is fluorine, which is a negative ligand having a charge of -1, monodentate. Then the metal here is cobalt with atomic number 27 again. So the configuration for this becomes 3d7, 4s2, 4p0, and of course 4d0. Okay, how many electrons do I have in D? We have 7 electrons in D. We have 2 electrons in 4s. Let us look at the oxidation number again. Assuming the oxidation number of cobalt to be x, the charge on fluorine is -1 each, and we have 6 fluorines here, so it becomes -1 into 6, which is equal to the overall charge, that is -3. Therefore, the value of x comes out to be +3. That means again, the metal, that is cobalt, present in this coordination compound will lose 3 electrons. Therefore, 2 electrons will go from 4s and 1 will go from 3d, making the configuration for CO plus 3 to be 3d6 and 4s0, and of course 4p and 4d are 0. Okay, now how many ligands do we have? We have 6 ligands, and fluorine is a weak field ligand. And we know whenever we have a weak field ligand, there is no pairing up. The electrons remain the way they are. So in this case, 3d6 will remain as it is. 4s0, 4p0, 4d0, all these orbitals, they are vacant, and we need to form 6 bonds, 6 coordinate bonds, which requires 6 vacant orbitals. That means 1 will come from S, 3 will come from P, and 2 will come from D, making the hybridization sp3d2 hybridization. And for this, the geometry is octahedral. Okay, do we have unpaired electrons over here? Yes, we do have unpaired electrons. Therefore, it is a paramagnetic coordination compound. Since the hybridization is sp3d2, we are using the outer d orbital, so it is an outer orbital complex. Looking at the geometry of this particular structure, that is the octahedral geometry for this coordination compound. That's all for this module. Thank you.